Good morning, fellow mathematicians. Welcome back to another video. I'm feeling way better, to be honest, and that's why we are going to make a big boy video about the geometric series, starting off with the finite case and going on to the infinite case, talking about its Taylor series expansion and then the radius of convergence, blah blah blah. It's going to be quite a lot of stuff, but I hope you are going to enjoy this video right here. In the finite case, would you even call this a geometric series? Because, to be honest, it's just an nth degree polynomial. It's not really a series. Series is the infinite summation of sequence members, so this doesn't make any sense when it comes to terminology. Never mind. What do I mean by the finite case? Well, it's just a finite degree polynomial. So let's call this thing S for a series. And well, it's like this right here. 1 plus r plus dot 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 up until r to the negative n to the n minus 1 plus r to the nth power. Okay, so this right here is just our basic geometric series, and what you want to find is a certain form of this thing right here. And for this purpose, I would just like to multiply this s right here by r. Okay, so this is really easy. If we multiply s by r, we are going to end up with, well, this is just r plus r squared plus dot 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 plus r to the nth power plus r to the n plus 1. Just distributing the r into every part up here. And why not? Well, take the difference of those two, so subtracting r times s from s. What do we get if we do this? So at first we get s minus r times s. Well, the good thing is s is a common factor, so why not? Well, factor out the s on both parts, so 1 minus r. And what do we get on the right hand side? So I want you guys to notice that if you subtract those two, then r and r is going to cancel out right here. R squared and r squared is going to cancel out, blah blah blah, up until r to the nth power. So all that's left is 1 minus r to the n plus 1th power. And if we don't take the number 1 into account, this thing right here isn't going to be equal to 0. So especially this 1 minus r part isn't going to be equal to 0. So why not divide both sides by 1 minus r to get a final expression for s, namely s is nothing but 1 minus r to the n plus 1th power over 1 minus r. And this right here is, well, our finite case for the geometric series whenever r is not equal to 1. So this is already quite good. What is going to happen if we take the limit as n approaches infinity? What is going to happen? So just taking the limits on both parts. Limit n to infinity of s. Well, on the one hand, we get this right here. So we are going to get more and more terms in this polynomial. So this is 1 plus r squared plus dot 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 up until infinity. We can rewrite this right here equivalently as the infinite summation from n equals to 0 to infinity of r to the nth power. Okay, so this is just the same argument right here, not talking about the radius of convergence at the moment. What about this side right here? Why not take the limit on this part right here? Is equal to the limit as n approaches infinity of, okay, 1 minus r to the n plus 1th power over 1 minus r. If we take n approaches infinity, then, well, this part right here is going to explode to infinity if our r is strictly greater than 1. If our r is 1, this wouldn't even work because, well, this was the restriction even on the finite case. But if r is strictly less than 1, then this is, for example, 1/2 to the nth power. And if we take the limit as n approaches infinity, this is going to 0. So whenever our r is between 1 and also negative 1, so even if this is alternating right here, negative 1/2 to the nth power, it's still going to end up with a 0 right here. So whenever this condition holds, we are going to get 1 over 1 minus r. Okay? Whenever our r is strictly between 1 and negative 1, we can rewrite this equivalently as nothing but absolute value of r being strictly less than 1. Okay, maybe this was quite some input, but this is basically it. So you see, we have taken the limit as n approaches infinity of this finite geometric series, and at the moment we got an infinite series right here, which is by accident already the Taylor. series expansion of this thing, and also we got this finite form right here, this definite form right here, this expression for the infinite geometric series. So this is already in itself quite good, but I want to prove that this right here is indeed the Taylor series expansion, and that this right here is indeed the radius of convergence. Okay, let's go ahead and get started. So remember, not really a Taylor series expansion, more of the Maclaurin series expansion. We want to find an expression for our f of x, which is nothing but 1 over 1 minus x, in terms of an infinite summation from n equals to 0 to infinity of, well, the nth derivative of f at the point 0 over n factorial times x to the nth power. This is what we want to find out. And if you take a closer look, we would get this expression if all our derivatives would be n factorial everywhere. So this is what we are going to find out. And by accident, yes, this function right here is basically the only function which is going to give you the factorial whenever you differentiate it. Okay, so f prime of x. What is this? I want you guys to notice that 1 over 1 minus x is nothing but 1 minus x to the negative 1th power. Okay, so differentiating that, we are going to drag the negative 1 down, negative 1 minus x, and we are going to reduce this power by 1, so to negative 2 power. But also we have to take the inner derivative. Inner derivative is negative 1, so times negative 1, which is going to give us, okay, negative and negative is going to cancel out to 1 times this chunk right here, but 1 is nothing but 1 factorial times 1 minus x to the negative 2. Next iteration, let's move on. F double prime of x is nothing but, okay, we are going to drag negative 2 down, 1 minus x to the negative 3 power, negative cubed, and then inner derivative stays as it is, negative 1. So negative negative is going to cancel out, 2 is nothing but 2 times 1, so this is 2 factorial times 1 minus x to the negative 3. One more iteration. F triple prime of x is nothing but, okay, dragging this down, negative 3 times 2. Okay, you see, this 2 is going to stay right here, times 1 minus x to the negative 4th power, negative 1 is nothing but, okay, 3 times 2 is the same as 3 times 2 times 1. So this is 3 factorial times 1 minus x to the negative 4th power. And I hope you can see a pattern here. It's not going to change even for the infinite derivative. So the nth derivative of our function is nothing but, well, n factorial times 1 minus x to the negative nth power. To the negative n plus 1th power. I'm sorry. Okay, this way. I'm terribly sorry. What is going to happen if we plug 0 into all those derivatives right here? Well, on the first part, this is just 1 over 1, but this is 1, and 1 is nothing but 0 factorial. So this is 0 factorial. If we plug 0 into here, this is just 1 factorial. If we plug 0 into here, this is 2 factorial, blah, blah, blah. So if we plug 0 into here, this is going to give us n factorial. So whenever we are going to evaluate the nth derivative at 0, this is just going to give us n factorial. And you see n factorial and n factorial is going to cancel out to just 1. So this is nothing but what we have already gathered. That was quite easy. What about the radius of convergence of this whole thing? Once again, we are going to make use of the ratio test. So we are going to take the limit, as n approaches infinity, of the absolute value of an plus 1. Our sequences an are nothing but those x to the nth power. So x to the n plus 1th power over an, which is nothing but x to the nth power. And the cool thing is x to the nth power and x to the nth power is going to cancel out. So we are going to take the limit of the absolute value of x. It's not with respect to any n, so the limit of this thing is nothing but the absolute value of x in itself. And in order for this series to converge absolutely, this thing right here has to be strictly less than 1. And this is what we already gathered. So this is one of the easiest Taylor series expansions you could possibly get, because you can see at a glance what this is going to evaluate to in the limit and under what conditions. So this is basically it. This is all I have to say about this little geometric series right here. And with this right here, we can actually calculate, for example, another expression for the Dirichlet kernel, for example. So this is something I'm going to do next. And I hope you did enjoy this video. If you did, please like, subscribe, and recommend the channel if you like. If you want to support the channel a bit more, you know how you can do this. And well, I guess up until the next video, have a geometric day. See ya. Lisa, wink mal. Doch, winken.